Okay, so this is going to be where we go through how to determine the charge on an atom. Okay, before when we were drawing the covalent structures of molecules, the assumption that you were making is that every atom that was going into the molecule was a neutral atom. So for instance, if I said draw a molecule that had 1 carbon and 4 hydrogens, you would start with the dot structures, and what you would say is that you would form a bond there, you would form a bond here, you would form a bond here, and you would form a bond here. So the assumption that you made during all this is that the fragments that you were starting with were neutral fragments. This right here, okay, this is the dot structure for neutral, okay? But what I'm going to do is show you some examples of molecules that have an overall positive or negative charge and how to determine whether there's a charge on the atom or not. One thing that you're going to need to be able to do is to kind of go in reverse. Let's take hydrogen, for example. When you made a hydrogen atom, okay, or a hydrogen molecule, you took 2 individual fragments and you made a bond. Okay, so you can do that, right? So what you're going to need to be able to do is to try to do this in reverse. What would happen if you said, essentially took some scissors and you cut this bond in half, all right? What you would be saying is that 1 electron would go back to this guy, 1 electron would go back to that guy, and this is what you would have if you cut that guy in half, okay? So we're going to be doing that type of mental exercise in these problems, all right? So let me start with the neutral molecule, and I'm going to, show you how to, prove that it's neutral. Okay, so here's that neutral molecule that we had before. Okay, so what I want you to do is to mentally break these bonds right down the middle. Okay. And what's going to happen is you're going to say, okay, so how many electrons were in that bond? Okay. So if 1 electron goes one way and 1 goes the other way, does it make sense that the fragments that would be formed would be, you would get an H dot from that guy, all right? On top, you would have that fragment. On the side, you would have that fragment. On the bottom, you'd have this fragment. And in the middle, you would have that right there. Okay, they look a lot like dot structures, but essentially it's like saying, okay, if that dot from that bond went to that side of the carbon, and so forth. All right. So so what you need to do is compare the fragment to the neutral dot structure. To neutral dot structures. Okay, and so really, even though these guys are all drawn with the dots on different sides, all these hydrogens are the same. All right, they're all hydrogen with 1 dot. So fragment. Okay. All of these guys are H dot, okay? And what you want to do is compare that to the neutral atom. Okay, so how many dots are around a neutral hydrogen? 1. Okay, so this is 1, this has got 1. Since they're both equal to each other, that means that those hydrogens were neutral, okay? Compare this carbon. Okay, so this is the carbon fragment versus neutral carbon, which has got 4. 4, so 4 versus 4, that carbon is neutral as well. Okay, the times when you're going to have charge is when this number is not equal to this number. Okay, so let me give you an example, show you a sample of something which has got a charge. All right, I almost drew the charge on there, but it's kind of habit. All right, so what you have here, this is called a formate ion. So this is a hydrogen which is single bonded to a carbon, carbon double bonded to an oxygen, single bonded to the oxygen. And the important thing to note is how many lone pairs there are around each atom. All right, this oxygen has got 2 lone pairs. This oxygen here has got 3 lone pairs. And lone pair is the same thing as unshared pair. I use those terms interchangeably. Okay, so let's break all of these bonds. Okay, so first, how many electrons are there in each of these bonds in the double bond? Well, like in the whole bond here. So does it make sense that this one here has 2 and this one has 2 as well? Every dash like that stands for two electrons. Okay, so if I were to draw the fragments that result from this hydrogen here would be like this. All right, and remember this is a fragment, not a structure. The reason I put that up there is I'm trying to show kind of geometrically, like if that dot went back on that hydrogen, he would have the dot there. This oxygen here would look like this. And then you would have this single electron here, which came from the breaking, the electron that he took from that bond. Okay? That oxygen on top would look like, okay, he would have 2 that were already there, 2 that were already there on the side, and then this guy here came from the 1 that came from that one. This guy here came from the 1 that came from that bond there. Okay? And then the carbon, he would look like, he would have, the 2 that came from these 2 bonds. He would have this one which came from that bond. And then this one which came from this bond here. Okay? So what you want to do is now take these and compare them to the neutral fragments. Okay? So let's start with this carbon. Okay? Okay? That's the fragment versus what's the neutral guy look like? Neutral carbon has got 4. Okay? 4 versus 4. He's neutral. All right. The next one, hydrogen, and you'll get very used to hydrogen. All right. Hydrogen's got 1 dot to it. Neutral hydrogen's got that. 1 versus 1. Neutral. Okay. This oxygen here. Okay, a neutral oxygen. A neutral oxygen has 6 electrons, right? Okay, 6 versus 6, neutral. All right, and now's the important one. That fragment here looks like this. Okay. That fragment here has 1, 2, 3, 4, 5, 6, 7 dots around it. Okay, you're going to compare that to what a neutral oxygen has, which is 6. All right? And so here's the logic. If oxygen needs 6 dots around it, or 6 electrons around it in order to be neutral, what if it had an extra electron? If it had an extra negative charge compared to what it needed to be neutral, that would make him negative. Okay, specifically he would be -1. All right, so all the atoms are going to be have one of any 3 charges. They'll either be +1, -1, or -1. All right. So what do we do with this information that he's negative? All right. The way you represent that in a molecule is you go back to the original molecule. I might have to redraw these bonds. Okay. And anywhere that you have a charge which is not neutral, you indicate that with a little plus or minus in the upper right-hand corner of the atom. Okay. The carbon here, we determine that he's neutral, so we don't do anything to him. Hydrogen, he's neutral. You don't do anything to him. This oxygen here, that came from this one. He's neutral, you don't do anything. This guy is negative. What you do is you go and you put a little minus charge in the upper right-hand corner of it to indicate that there's a -1 charge on that particular atom. Okay? Does that make sense? All right. So let's try it on a different molecule. Okay, so try to do that little thing where you go and you kind of break through all these bonds and see what the fragments you would have are. All right, I'm gonna go ahead and do it here, and I'm gonna also talk about a couple shortcuts. The one thing that you'll notice is that each and every hydrogen here is single bonded, all right? And you're going to learn this little shortcut, is that if a hydrogen's got a single bond to it, it's going to be neutral, all right? The reason for that is when you break that single bond, the fragment that you get from that hydrogen is just a hydrogen with a dot, all right? A hydrogen with the dot is always going to be compared to the dot structure for neutral hydrogen, all right? 1 versus 1, okay, neutral. Okay, so you can do this to prove to yourself that hydrogen with a single bond is always neutral. But if you just get used to, if I see that hydrogen with a single bond, I automatically know it's neutral and not want to do this. That's fine. So all the hydrogens are neutral. That carbon right there, his fragment would look like this. He's got a dot here, he would have a dot here, he would have a dot here, and you might be wondering why am I using this type of spatial relationship? It's because up here this carbon's got a bond that's kind of angled out that way. This dot right here represents the electron that he got when you chop that bond. This one is from that bond, this one is from